Hello, everybody. Thank you for your attention and attendance of my talk. So today, I know for this workshop, there are three, in the title of the workshop, there's three words: inverse problem, PDE, and machine learning. So for my talk, I'm going to temporarily not include the last one, machine learning. I will have PDE and the inverse problem. So it's mainly focused on the first two. Just let you know, if you're expecting something machine learning, that's something not included in this talk. This is what I'm going to present is a combination of several work together with many collaborators: Daniel Apollo from Colorado University Boulder, Matt Dunlop from Courant, Bjorn Quist from UT Austin, Quirin from Columbia University, and Alex Townsend from Cornell. And so although I'm mainly talking about seismic inverse problem, which is about find oil and gas down the earth, but it's just one particular inverse problem that I know very well that can apply easily to all other techniques. But what I present is not just limited to seismic inverse problem or wave inversion. You will see in a minute. So let me start with the general framework of inverse problem. For no matter inverse problem, if you consider machine learning neural nets as inverse problem or as what PDE motivated inverse problem, we want to know the model parameter M. So the model is either a PDE or a neural net, and there's some parameter that we want to learn in the middle, either the weights or the velocity or the density of the PDE. And we have a lot of pairs of data, especially for large scale problem. We won't just have one pair of data. We will have a lot of pairs of data. Like X is the input we put into this model, and we get output Y. So we have a lot of pairs of them. And our ultimate goal is to use this input and output pair and try to reconstruct what the model parameter M. This is the general framework of the inverse problem. And for this framework, first of all, if it's physical motivated, we need to make sure which PDE we are talking about that really for this application. And if it's machine learning, probably the first thing we want to know is this going to be convolution neural network or residual neural network or a GAN model? So that's the first thing we really want to know first before doing any inversion. And for some of the inverse problem, this model is given and we just find M. For example, for me, I want to do wave inversion. So the forward model is really the physics of wave propagation. There's not too much freedom I can do here. It's already given. But for the other subsets, for example, for machine learning based inverse problem, you have a lot of freedom to change your model. Maybe it's the same input output. You can use logistic regression. You can use scan. You can even use an ensemble of them. So for that type of category, F is not known, and your parameter really depends on how you construct your model, like how many nonlinear layers, how many linear layers. So there's like two different types of it. So for the part that F is given, for example, PDEs, we know this application really follows this physics and it really follows this PDE. The good thing is we really know the forward problem is going to be accurate. And the bad thing about it is like the map, naturally the physics give us may be very nonlinear. So when we try to do the inversion, it's not very easy. We will come across like ill-posedness, that's the language we use in inverse problem, or like local minima if we think about from optimization point of view. So that's the bad part about an explicit forward model that already known. And for machine learning, for example, F is not known. It's actually up to us to design. So the bad thing is, in order to find a very good model, it takes trial and error. For example, it may take a decade until one day we found out neural networks seem to be the one that match a lot of the data and to generate well. That's the bad part. It will take long for us to discover the model. But the good thing is, once we have some good idea, we can actually modify it. For example, we realize if I over-parameterize the neural network, I make thicker or make a lot of parameter over there, it behaves better. So that's the part that we can change the model. But that's exactly what the PDE equations doesn't have, because we don't have the freedom. We cannot change physics. That's quite dangerous if it's a physics-based application. So in my mind, there are two types of inverse problem. And for both of them, there's a good part and a bad parts. And for my application, I was mainly focused on the first part, which is a PDE motivated or PDE constrained inverse problem. Okay, so the particular inverse problem, like that I always try the techniques on, is seismic inversion. And I think in our first day of the workshop, the second talk by Matty Lutz, he was already introducing this kind of wave inversion. So for seismic inversion, it's basically about earthquake and about oil. So we want to know what's going on under the earth, beneath the earth, beneath our ground, but we don't know. So what we know is that if I have an input, which is my source, and the source propagate wave, and the wave will go back to our surface and captured by those sensors, and those are my Y. So what I have is one source with a bunch of Y. And if I change my location of the source, for example, put it here, then I will have another X and a Y pair, usually hundreds of them. So that's the information we know. And the information we want to find is what's going on under the ground, what's their velocity at different parts, and what's the density. Usually different velocity and density will tell us a lot about this material. For example, maybe it's oil, maybe it's salt, maybe there's something else. So that's how we find it, based on the velocity mainly. And the problem, if I give you more visually, like a presentation, is that we only have this kind of data that in the waveform. So the black-white Vigo represents the wave that we recorded. So wave have two dimensions or more dimensions. So it's in both time domain and the location domain, so spatial domain. So that's the wave solution. We have the wave solution in these two spatial and time domain, and what we want to reconstruct is the velocity, which is just in spatial dimension. And for example, this is the Mammoothy model, sort of like a benchmark in seismic community. So we want to reconstruct all the details of this Mammoothy model, like where are the layers and what's the velocity of the layer and the changes like that. So that's the ultimate goal. And since this is wave-based, so we have a very good, accurate forward model. We know that if you give me a velocity model, for example, if you give me this Mammoothy, and I can do numerical simulation of the wave equation by finite difference, finite element, spectral methods, DIIS, like all kind of numerical methods. If you give me the velocity and give me the source, I can compute the wave equation numerically, which is the forward problem, which means I have M here is our velocity. And I know how to find the wave solution U. And since the realistic case is I only have U on the surface, so I have partial data U on the partial boundary. And the inverse problem, which is what application driven that we want to solve, is that what if I only have this wave solution partially on the boundary, and I want to do the opposite of the forward map, that I want to find where is the velocity. So that's the inverse problem that we are concerned about. And as I said, since this forward problem is already given by either acoustic wave equation or elastic wave equation or more complicated and accurate models, I cannot really change the property of the forward map. And I also cannot change the property of the inverse map. And there have been a lot of theoretical analysis that both F and G are highly nonlinear. So since it's highly nonlinear, I cannot write it down explicitly, and I cannot really find the inverse function explicitly. And also because of its large scale, so we put it into an optimization framework so that we can still find a way to find an optimizer or the parameter we think is most probably to be the truth. So we formulated into a PDE-Constrained Optimization. So nowadays, a lot of those inverse problems, especially engineering-driven, they really need an answer. They will formulate it as a PDE-Constrained Optimization. Because for this one, we may not have a solution. But once you formulate it as a PDE-Constrained Optimization, and it become an optimization problem, and it must have a minimizer or multiple minimizer, then the existence is guaranteed. So that is a relaxation of the original problem. And in order to solve it, to get an answer, we majorly deal with this formulation that try to find the optimal parameter M So G, let's consider is the true data, and F of my M is the simulated data based on our current prediction. And I want to minimize the difference between the current prediction generated data versus the true data, and so that the model that give me the minimized objective function will be the optimal solution. So that's the setup. It's very similar to the all the optimization setup for like even machine learning or other type of PD constraint optimization. And for our wave problem, the forward problem or the forward constraint or the state equation is the wave equation. So what I put here is the acoustic wave equation. This term should be 1 over c squared. C is the wave velocity. But in this community, sometimes we just do a change of variable to denote m as 1 over c squared. They actually give m a professional name is squared slowness. So instead of finding c, it's equivalent that we just find m. So this is this entire forward problem. And more details was reviewed in Mathilas's talk on Monday. So that's the forward problem, and I want to do the reconstruction. So when we want to do the reconstruction and we can do optimization, from my point of view, there's actually 4 parts that we can do something about it to make it better or try to reconstruct the better solution. So I think, first of all, the forward model, as we see, is given. So there's not too much thing we can change over here since it's PDE based. And the next step is to choose what will be a good objective function. Like different objective function, as you will see later, actually can give us very different results in this constraint optimization problem. So that's one thing. We need to consider if it's going to be convex, if I'm going to use gradient-based methods. And other than the objective function, we may want to add a regularization. And the regularization, that's the part that I have particular bias towards a certain structure of solution, or I have particular I want to smooth the solution. I want to piecewise constant TV regularization. So that's more like the expert point of view to have a bias to use certain type of or subset of the solution. And when we really do the optimization algorithm, there's also a lot we can choose over there. If it's a small problem, the idealistic case will be do global optimization. Then we don't have to think about convexity. But especially for this large scale problem, for like we want to reconstruct the Earth, the scale that we solve the wave equation is huge. And similarly with machine learning, there's tons of parameter over there. So global optimization is not really feasible to achieve a good solution in finite time. So most of the time we use gradient and Bayesian driven based optimization. So use local information of that point to do optimization. Then we run several times, several hundred or several dozens of iterations until we converge, and then we convert to certain solution. But if we don't know the truth, a natural question will be how much do we trust the thing that we get, and what will be the criteria for us to trust. So that's the 4 things I think is doable, or we can try to improve the final result of this optimization in the end. So let's first look at the objective function, what we can do about it. For this particular problem, or for many other inverse problems, when it turns to PDE constrained optimization, the objective function or the most natural objective function to use is the least square norm, because least square norm is easy to calculate and its gradient is also easy to calculate. So this is the least square norm that we do in time domain. But for this particular wave inversion, this problem is nonlinear, and when we squared it, we get a non-convex functional. So this objective function under the least square norm is non-convex, which for sure we will suffer from local minima trapping. Gradient 0 points may not be the optimal points. So that's the number 1 big challenge in this entire community is about local minima trapping, how to get rid of it if we don't know the truth. Second is sensitivity to noise. So if my G perturb a little bit, then that noise will be also part of my objective function. Then I may have the problem of overfitting the noise. Or on the other hand, my reconstruct solution will have perturbed noise input as well. So that's two major challenges that all L2 norm suffer no matter what application we are using this objective function. So what we did about this part is to introduce the Wasserstein distance. So for Wasserstein distance, actually on Monday and Tuesday, there have been at least 2 or 3 talks that involve optimal transport and Wasserstein distance. And what I present here is just another application that where we can use optimal transport. It's a little bit different from what machine learning community use it. And here, how I use it is basically just as a measure of mismatch. So if we look at this 1D wave equation, since it's a constant velocity, so we can get an explicit solution by D'Alembert formulation. So the D'Alembert formulation depends on my velocity parameter m. And so we can look at if I have some perturbation in my velocity parameter, what it looks like in my data. Because what is observable is the change in the data. So when we have perturbation in m, we can see that a perturbation in m will give us translation if we fix x and just see t, because the solution is in both time and spatial domain. If we fix spatial domain and we see translation in the signal. Okay, if I fix the time and I just look at the spatial domain, what I see is dilation. So this simple motivation tells us if I don't have the correct velocity parameter in the model, what I can see in the data is translation in the data and the dilation in the data. And we want to ask ourselves, is this kind of change directly related to the model change, but is this type of the change that can be captured by the L2 norm? And the answer is no, L2 norm is not going to capture shifts and the dilation. And that's the whole motivation at the first paper by Enquin Frost to introduce the quadratic Wasserstein distance. So here I present 2 wavelets, the blue one and the red one. And I want to measure the difference between these two. And you can see over here, the difference is only purely shift. And if I measure these 2 signals in terms of L2 norm and also plot it as a landscape in terms of the shift, it's 0 when these 2 signals coincide. But we see a lot of local maximum and a local minimum because of this translation. It cannot capture the translation. And when these 2 signals are totally separated from each other, we get landscape constant, although they are really further away. But at the same time, if we measure, nothing gets changed, but just measure it by a new method. For example, the quadratic Wasserstein distance or the L2 Wasserstein distance. What we get over here is a totally convex landscape. So although this example is very simple, but this kind of phenomenon shows a lot in this particular application that if I don't get correct velocity, I see shift in the signal. And the shift can be captured, can be reconstructed by the Wasserstein distance. So that's why we introduce quadratic Wasserstein distance as a measure of mismatch. So we translate the waveform into one of the density functions, that's G, and we transform the predicted synthetic waveform produced by our prediction of the velocity, and that make it another probability distribution. And we measure the difference between these two by the Wasserstein distance. And we get this global for this simple case, we get global convexity. So optimal transport is already mentioned several times. Here, I just want to give a cartoonish kind of introduction. And that's also the motivation why we stick with this idea for so many years. Consider that we have two signals. They are not the same. And we want to measure how different one is away from the other. So there are many ways to measure them. We can use L1 distance, we can use L2 distance. But what Wasserstein distance is doing is moving the extra mass from the first bin to the second bin. Because they are probability densities, so there's a conservation of mass over there. A little bit rearrangement will make them exactly the same. So now doing this rearrangement, distribution map into another distribution, total mass conserved. And after this map, we have these 2 signals look the same. And then now we want to measure what's the difference or how much effort we made in order to make them the same. And the measure of difference is the amount we moved multiply the distance we moved square, because we are using W2. And if you use W1, this will become just distance. So when you compare signals using the Wasserstein distance, you get at least the 2 dimension or 2 coordinates of comparison. One is a coordinate, is the x-axis. It's like the input axis is the location. And another axis that is comparison is the vertical axis, is the intensity. So in the language from the wave part, is that Wasserstein distance, when measuring waves, it can measure both the phase and the amplitude. While under the L2 norm or L1 norm, what we get mostly is the intensity or the amplitude difference. But when we use W2 norm, we get the global comparison. And that's why we use it. That's why you can see the convexity at the beginning in the first several slides ago. And also we have proved that for Wasserstein distance, if we have a fixed signal G, which is a density function and is smooth and nice enough, and we can do a translated and dilated version of G. So F theta is basically a translation and a dilation, a combination of G. Although it looks complicated, we just try to parameterize the dilation and the translation in every dimension. So if it's a D-dimension signal, then we have 2D parameters. And if it's a 1-dimension signal, we only have a translation and a dilation parameter. So F theta is the translation and dilation of G. And if you use the Wasserstein distance comparing these 2 signals, it will be a function of those translation parameter and the dilation parameter. And we prove that it's going to be globally convex in terms of both of them. And that's the motivation that we use the Wasserstein distance and try to create a better optimization landscape. It's unfair to say that it's convex all the time because the real signals are quite complicated, and we also have normalization on top of it. But it will be more convex than the original least square norm. And I think it will be more convex than most of the LP norm. So here I just want to show you inversion results. We start with the almost homogeneous, smooth initial gas. And as the iteration continues, the velocity on the first row are updated iteration by iteration. And what you see in the bottom row is actually the residual. So what I mean residual is the difference between the true data, the difference between the true data and the synthetic data. So let me play it again. And the first column is the L2-based inversion. And the second column is W2-based inversion. So they are both, the iteration number are both increasing. But W2 is increasing to the Mammoothy model that we see at the beginning of the talk. And L2 inversion convert to something doesn't really make any sense. And also, if you look at the residual, we translate this inverse problem into a data matching problem. And we want, in the end, data to be matched. But the L2 inversion, after 300 iterations, still a lot of difference between F and G. That's why we can see this residual down there. But for W2 inversion, most of the residual are gone. If we look closely, there will be very tiny left over, but most of the residual are gone. So we really did complete the task of data matching. And the second motivation of using Wasserstein distance is actually more robust with respect to noise. And the justification from its robustness with respect to noise can come from its analytic property between W2 and H-1. So here I just briefly define the H-1 dot, the dot H-1, weighted H-1 norm by this Laplacian type of linear operator. And we call it weighted H-1 because it is weighted on this measure F. If F is 1, which means we are doing the big measure, then it's exactly the H-1 Sobolev norm that we are familiar with. And here is a little bit tiny difference. It's a weighted H-1 because the integration here is with respect to this measure F. And by analysis, and this is from the optimal transport side of analysis, that we have this following result. Basically, it's saying when we have two probability measures and they are really close to each other, then W2 is asymptotically H minus 1, weighted H minus 1. This has been done by Villani and Otto in 2000. So we know that asymptotically H minus 1 is W2. And even if F and G were the two probability distribution we are comparing, they are not close enough, we can still bound the Wasserstein distance by the H minus 1. If we know this two distribution has an upper bound and a lower bound, C1 and C2, then we can still bound W2 by H minus 1. So these two equations actually tells us a lot about the connection between the W2 distance, which come from optimal transport, versus the Sobolev norm H minus 1 that we are familiar with, that we used a lot. So this is the connection. The next, let's see, what if I use H as norm to do optimization? What I can gain compared with using L2 norm to do optimization? So we can see the effect just by looking at this linear problem, A M equal to G, and I want to reconstruct M. And unfortunately, my G is polluted by some noise. So it's noisy data. And A is a diagonal inference domain. We have this assumption so that it's easier to analyze the modes that affect on the solution M. Then if we use general H as norm to do the inversion or to do the constraint optimization, you will see that we can, since HS has relation with the Fourier domain, so we can rewrite it in terms of the Fourier domain, which this G hat and F hat are the Fourier transform of F and G. So, and the C is the frequency mode in the Fourier domain. So that's our objective function. Since this is linear and the HS can be seen as like a least square, weighted least square base. So we can write down the solution M explicitly in terms of the frequency. So this frequency mode of M can be expressed by the frequency mode of my operator A and also the frequency mode of my data G. So this equation in right tells us how this mode from the operator and the mode from data can affect the mode of the solution. And if we take an inverse Fourier transform, we can get back the solution in the physical domain. And this is what we look like. And it looks like exactly like a weighted least square solution. And then the P is actually come from the Laplacian operator. And the next is the thing that gets interesting. If this S is 0, which means it's H0 norm, which is L2 norm, then we are not biasing anything in this noise. So the noise here, we don't have any bias. But when S is larger than 0, here we are actually, this C to the power 2S is actually emphasizing the higher frequency of the noise mode in G delta. And when S is less than 0, I'm actually having a weight of 1 over C squared that I'm emphasizing the lower frequency of the noise mode in this G delta. And since noise, most of the time are high frequency noise, so when I choose S less than 0, there's a smoothing effect over here. So that those kind of noise is now going to be seen once I have this weighting in front of it. In another word, using negative norm in data matching, we are getting a reconstruction that without that much of noise. So it's like each negative norm will be robust with respect to noise. And that's another point of view to see why we use W2 norm, and we can see this insensitive to noise phenomenon over there. That's the second motivation but more general from W2 to general H negative norm. And again, I'm not saying H negative 1 is the same as W2, because by this paper from 2013, we can see the geodesic in H minus 1 space and the geodesic in W2 space look quite different. The first row is the geodesic change or interpolation in H minus S, in H minus 1 domain, geodesic. And the last row here is W2. So W2, you can see here is clearly purely a transport. But for H-1, there's a change, but there's more like a local behavior as well over there. So I think there's more to investigate between the difference between H-1 and W2, and it's unfair to say they are exactly the same. They may be the same if you look closely in the linearization regime. Okay, so using W2 distance or using general HS norm in optimization, we are actually doing a type of regularization because I already have, if I use H negative norm, which means I want a smooth reconstruction. And if I use H positive as norm, it means I want to emphasize a higher frequency in the data. So I want to build more higher resolution reconstruction. So regularization can be implicitly enforced by the objective function. So the second part we can do. And the next part we can do is optimization algorithm. For example, how fast can I make it to converge? And for my problem, we use gradient-based optimization algorithm because it's too expensive to do global optimization. And if I already know I'm going to use gradient-based method, basically I admit I'm going to achieve my solution at gradient equal to 0. Then the question is, can I make it faster? So there's a first order method like steepest descent, gradient descent, and there's a second order method, and there's something in the middle, Newton's method and the quasi-Newton method. There have been a lot of talks this 3 days on acceleration method, either for neural network or for general inverse problem. What I want to bring up is another acceleration method. I think it's quite simple, and maybe it can help your problem a lot. So this needs us to look at gradient descent from the other perspective. So this is the fixed step size gradient descent formula. And it's like the right-hand side is PK, and then this is the gradient evaluated at the PK. So the right-hand side mainly depends on PK, or just depends on PK. So I can view it as a nonlinear operator on PK. And when I stop, is that whenever I give the right-hand side PK, I get the same thing, which means I stop when the gradient is 0. So basically, we are seeking the fixed point solution of this operator G. So by writing it in this way, I'm viewing steepest descent as a fixed point operator. And what we are searching, if we just use gradient descent, is actually the fixed point solution to this nonlinear or linear, depends on the J, to this fixed point solution. And what we are doing if we fix the step size is basically Picard iteration for fixed point operator G. If we don't do anything, that's pure merely gradient descent with fixed step size. And the question is, if I view it in this way, can we do better? So the perspective that I think we can do better is to speed it up as we speed up fixed point operations. And this is the tool that I used, Anderson acceleration. Anderson acceleration is it was brought about very long time ago, 1965, and it was reinvented in the context of quantum chemistry by the name of DIIS and the Pulay mixing. So the main idea for this Anderson acceleration is each time I do the fixed point iteration, I produce a new solution. And usually you will just use PK to give you PK plus 1 and the PK plus 1 to give you PK plus 2. But we don't use PK and to give PK plus 2. And the Anderson acceleration is saying that I'm not going to ignore all the previous iterates, but it's too expensive to remember all the iterates. How about I have a short window? So I have a window of size m. I'm only going to remember the m previous iterates. And my next iterates, PK plus 1, is going to depend on all those m iterates. So it's like a extrapolation method, but it's like a changing window all the time. So it's like, from my perspective, it's like a limited window GMRS to some extent. So this method is very simple because the only cost is to find those weights that optimally combine all the previously m iterates. And this way, this is like if you use 2 norm to find the residual, to minimize the residual, then this will be just a least square problem with a very small size because usually we choose M to be 10 or 20, and it's very small size least square problem and very easy to solve, basically for free. So we don't have to construct inverse Hessian, but this can equally achieve something like a multi-secant method and a superlinear convergence. There have been many literature over there prove the convergence. So it has a lot of connection with GMRS. It's exactly GMRS if we have M equal to infinity. And it's related to multi-secant methods. And a lot of the bond we obtain is related to Krylov space methods, like the bonds look like CG bonds and look at related to Chebyshev polynomial. And it's also related to momentum method, and it gives us superlinear convergence if G is contractive operator. And what's amazing is even if the G is non-contractive, which means P-car will never give us a contractive solution, and there's an acceleration on top of P-car, sometimes can give us the convergence. So that's why it's very popular in engineering to accelerate your fixed point iteration. And I also use it for my problem, which is wave inversion. And I compare it with the behavior of stochastic gradient descent, the SD, and the conjugate gradient, nonlinear conjugate gradient descent, CG, and LBFGS and AA. So if I use not the number of iterations, but how many times I have to evaluate the wave equation, it actually beat up those quasi-Newton methods. Although LBFGS and CG may take smaller iterations, but in order to get the optimal step size, I have to do a lot of backtracking line search. And each time I do backtracking line search, I have to evaluate my forward problem and the adjoint problem to get the gradient. So that's actually a lot of CPU time. But if I just look at CPU time rather than the number of iterations, A has a winning side in the computational cost. So next, if we have done all this, then finally we have our solution. Then the question is how much we trust the solution. One thing we can do is to look at the objective function. But in reality, in practice, rarely we can really reduce the objective function to 0. So that's not a really effective measure to look at. So that's the situation. I think the Bayesian approach actually can offer us a lot of insights in this aspect. How much do we trust the solution? Because in the Bayesian approach, we have exactly one component dedicated to that part. It's about uncertainty quantification. So if I still want to solve the problem with the wave problem, but I'm going to use the Bayesian approach, this is the 4 components, I think, what we can do to improve the final performance. The choice of the likelihood function, the choice of the prior distribution, the sampling method, and also finally we will do uncertainty quantification. In most of the time, these 2 components won't really matter that much. The prior distribution won't matter as long as we have enough data. But for large-scale problem, that's not really the reality. That's when primary distribution, the choice of prior, really affects our final result a lot. And also likelihood function. In the past, we have been using likelihood function based on the assumption that the noise is additive Gaussian. But this is just one particular assumption which can be changed. And we did some work with Ahmet Dunlop, and we discovered that likelihood function change can actually also affect our posterior distribution a lot. So let's first look at the likelihood function. So this is like a summary of what we analyzed in the paper. So what everybody is most familiar with is we consider the data is additive Gaussian noise. So eta here is a noise model. And if you think this is if you agree with noise model as this, the likelihood function you get is correspondingly to be the L2 type of likelihood function. Okay, if you change the additive noise a little bit, instead of making things think it's just white Gaussian, I think it's Gaussian with this correlation matrix, covariance matrix. Then it's not L2 norm anymore. It's actually H-1 norm in the time domain. And if you think it's some other covariance matrix, and the corresponding norm will also be changed. So there's a lot of freedom over there, but based on our assumption. So the main thing we did is to analyze if I use the Wasserstein distance as the likelihood function in Bayesian inversion. what exactly the noise model I'm considering. So it's natural to think this is a potential, and why not just use this as my likelihood function. But I know for Bayesian people, what they really care is why this choice. And we analyze that if you use the quadratic Wasserstein distance as a likelihood function, we are actually assuming that there's a state-dependent multiplicable noise data model. And it's state-dependent because it depends, so the covariance, so eta is a multiplicable noise, and the covariance over here, depending on this Laplacian operator L. You can see more detail in the paper, but it's state-dependent. And in some other contexts, people have been using multiplicable noise as well. And if it's not state-dependent, for example, eta follows normal distribution or 1 over eta for normal distribution, the likelihood function is actually equivalent to this divided version of the least square norm. So I'm offering here because I think most of the experiments we have in the past has been the first row, but other choice of likelihood function will also make the inversion result, at least my point, look quite differently. So that's the insight over here. And the second is about prior distribution. And the prior distribution is corresponding to the regularization in the deterministic inversion, but still it matters a lot over here. What we do for this particular method is to combine with this level set prior. Level set was a method developed in 1980s and 90s that has been popular in imaging techniques. And the recent years, Dunlop, Stewart, this group, they have a lot of paper on how to use level set as a prior. So the first picture are samples from Gaussian prior, and the second picture are samples from level set prior. And for our physical problem, it will be more realistic if I can do a combination of these two. So this is the third picture over here shows the mixed prior, that the background is Gaussian, but there on top of it, I have some level set. And this is more like what the realistic we know about geophysical underground, because sometimes they have salt and sometimes they have smooth changing background. And the amazing thing in this approach is that we don't really have to know this constant. So for level set approach, we don't know the boundary, and we can gradually reconstruct the boundary over here. But we don't even have to know what is the constant over here. And that's more realistic and give us a lot of freedom to do the reconstruction, because in reality, we don't know the constant. We may know it's going to be a piecewise structure, but we don't know the constant. And if the constant can be also reconstructed together with the boundary of the level set and together with the background, that will really fit the realistic situation. So the experiment I'm going to present is this salt body reconstruction. And you can see on the background, we have a smooth velocity. That's where we will use Gaussian prior. But on the top, there's a salt body. So salt body has high contrast. That's why the velocity is much higher than its neighborhood. This is V, and what you see over here is the state parameter U. It's a transformation of V. And our goal is to reconstruct this velocity picture. And what we start with is nothing. We don't know the background, and we don't know this salt existence of the salt. And I want to tell you a little bit more like why this problem is difficult, like why reconstruct this picture is difficult. That's due to the property of this inverse problem or property of this wave propagation. First of all, for seismic inversion, we only have, if this is the velocity, we don't have the data on this boundary, or this boundary, because they are Earth, and they are just the entire part of the Earth, and there will not be any data reflected back to us from these three boundaries. And also, since these are part of the Earth, we won't be able to really detect what's going on in the middle. So the only thing we can get is a few points, a few locations on the top. That's the part we can get. So the available information for us is just on this boundary at a few, like 100 or a dozen, several dozen of locations. So our data is very, very limited. And on the other hand, we want to reconstruct the entire thing. And also when there's a discontinuity in the velocity, if you are familiar with wave, when wave propagate from the center and reach a discontinuity, it will generate a reflection. It will go back. Some energy will go back and some energy will keep propagating. So when it reaches the second layer, it will still some energy reflected back, and then some will keep propagating until they are really small and it's gone and never reflected back. So now what I represent,
Yunan, you have 5 more minutes.
Okay, I'm almost done. Thank you. So for this velocity, we see 4 different velocity models. They have different thickness. So they look visually very different from this slide. And this is the model. And in the next slide, I will show you how the data looks like. So this is the data we get by solving the wave equation with this velocity model. So although this 4 model looks so different, especially the thickness of the third layer, but what we see over here in the data, they look extremely similar. So if the data look extremely similar, it's really insensitive to see the thickness of the layer. So that's the main difficulty of reconstructing this kind of image, because we can know there's an interface that gives us this scattering, but we don't know how thick is the interface. And that's almost impossible if we don't have any wave that goes through this entire area. Okay. And here is what we can get by deterministic inversion. The first picture is by the L2 loss, and the second one is by the W2 loss. So W2 was what I engaged in for my entire PhD thesis, and we proved several results. But still, with this challenging problem, what we can do is a little bit thicker than L2, but still it's very difficult to reconstruct the entire solid body because we only have this reflection. So this reflection, it's not hard to tell there's something, but it's really hard to tell how thick is this interface. It's either this thin or either this thick. Doesn't really make a big difference in the data. So that's the difficult part. And these 2 examples come from the deterministic inversion. And it's the same set of data, everything the same setting. But if the next picture come from the inversion using Bayesian approach with the level size prior. So when we have the level size prior, we assume that we will see this structure, and this somehow give us a lot of more information and a lot of more bias. And in the end, this is a reconstruction. This is the map estimate, and this is the mean, and this is the standard deviation. At the beginning, and also we didn't do a lot of sampling. The update direction were mostly motivated by the gradient. So the total computational cost between this picture and the previous picture are almost the same. So cost-wise, using this Bayesian approach, I didn't pay too much, but I get a much better result, which I was very impressed, because just by reflection, just by the pure physics, we are not able to reconstruct the entire solid body. So that's one aspect. Another aspect is the standard deviation. The standard deviation tells me something about uncertainty quantification, or you can treat this image as how uncertainty I am about different part of the area. So you can see we are a little bit uncertain about the solid body and very certain about the background, and a little bit more uncertain about this area. So at the beginning, my collaborator was thinking why this is uncertain. And when I see this, I feel it's very physical. Because if you look at this truth, there is a piecewise this is discontinuity in the velocity. And theoretically, we can reconstruct this. We know there's something, but we are not sure how thick it's there. And in this standard deviation from the Bayesian results, it tells me this part, I'm not sure. Maybe it's this thick, maybe it's thicker. That's because the reflection hard to reconstruct thickness of the layer. Well, this information is also illustrated in the standard deviation, and that will be how much we can trust the result we get. Maybe if I'm a geophysicist, I will be a little bit skeptical about this part and do more investigation or do another inversion. And that's the extra piece of information that Bayesian inversion can offer us, while deterministic cannot. So that's the final component of the uncertainty quantification. So the main takeaway message from my own experience and my talk is that for this large-scale inverse problem, either seismic inversion or other type of inverse problem, I think a combination of both the deterministic approach and the Bayesian approach will really help us to achieve the best results. And these 4 components about Bayesian approach and these 4 components about deterministic approach, they are one-to-one correspondence. And so I think in the future, if the computational cost of doing Bayesian will be easier, will be cheaper, we can really update our current state of the art. So that's the end of my talk. Thank you very much for your attention, and I'm happy to take any questions.